Hello everyone and welcome to my presentation. My name is Abhishek Shende and I work at Brilliant MD and University of Texas at Austin. My talk is on the topic of network design for social welfare. My co-authors on this paper are Deepanshu Vasal at Northwestern and Dr. Sriram Vishwanath at University of Texas at Austin. This talk is being presented at Conference on Information Sciences and Systems, CISS 2021. This is my presentation. So the growth of connections between people in various settings like economic, social, commercial has motivated the study of how interactions between linked members affect the outcomes. Network games have been used in such settings to study these interactions where the actions of individual players is affected by the actions of its neighbors. And these have been applied for real world settings where there are tons of connections between members. In such games, there is an element of designer influence where the designer can manipulate the game result through policy framework or control action. In other words, the designer can arrange the interactions between players and get the desired result, or through the changes in payoff function could get the desired result. This investigation into the underlying networks that promotes social good for rational players requires understanding which network structures are beneficial over others to achieve a community benefit. Subsequently, in this talk, we are interested in the following questions. What kind of network are good for the society, and how to design such networks? For these purposes, we assume a linear quadratic game model, which is also known as the LQ game. This model is very popular in studies of network games in the past. Here we assume a network game with n players. Their interactions between these players are presented by the adjacency matrix G. In this matrix, we assume that the diagonal elements are zero, that is, there is no self loops. This adjacency matrix has the interactions between the different players. And each player I chooses a strategy given by xi, which is a positive strategy that minimizes the cost function. This cost function is linear quadratic as seen in equation 1. It has it is the function of its own strategy xi, as well as the strategies from its neighbors, which is an aggregate effect presented by the term zi, which is the sum of gij xj over all j's. And then there is a constant term ai, and together this represents the cost function for an LQ game. So as we know, a Nash equilibriums are the set of activities within which no player has an incentive for unilateral deviation. That is, each person is playing for the best response to the other player's actions. In our case of cost function, we define it as the minimization for the cost function with respect to its own strategy. So for the LQ game with the quadratic cost function, we can derive the Nash equilibrium x star by using the first order condition, and we can present it in the matrix form as shown in equation 4 as I plus g times x star is equal to a, where I is the identity matrix. For the social optimum, and we define as the strategies y star, which minimizes the individual social cost functions. So the social cost for an LQ game is defined as the sum of the cost functions for each player playing in the network. So that is shown in equation 5. where we show that the cost function C is the summation of the pay of the cost functions Gi. And then again, the social optimum y star, which is the minimum, can be derived from first order conditions. And in matrix form, it is represented in equation 7 using I plus G transpose times y star is equal to A. So as we are interested in the network design, we are talking about a network where, presuming strategic players play selfishly, the Nash equilibrium of this resulting game coincides with the designer's objective, which in our case is the social welfare. So from the derivations in the previous slides, for the Nash equilibrium to coincide with the social optimum, we want x star is equal to y star. And using the results, results from the previous slides, we have equation 9, which is I plus G times x star is equal to A and G transpose x star equal to 0. These conditions give us help us find networks which can give us socially optimum Nash equilibrium. Based on these observations from equation 9, we can see that where since G transpose X star needs to be 0, and X star is not 0 and is positive, G transpose is not invertible. Um, since and determinant of G is 0 is a necessary condition for finding a network with socially optimum Nash equilibrium. From this, we can also see that one of the eigenvalues of G has to be 0. For symmetric G, we also observe that the Nash equilibrium and the social optimum, when they coincide, have the value of A, so they don't depend on other factors of the adjacency matrix. And in an LQ game, when the matrix is symmetric, that is Gij is equal to Gji, an exact potential function exists, which allows the use of theory of potential games for symmetric matrices for studying the social optimum Nash equilibrium. Here we present a numerical example for n equal to 3 players. We have assumed some cost function for the LQ game with the AIs as shown, and some of the interactions being assumed. Based on these conditions and then the equations derived earlier, we can find the necessary interaction terms between all the other players and find the socially optimum Nash equilibrium as shown here as X star. For another example, for n equal to 4 players is shown here in which case the adjacency matrix G is symmetric. And we can see that for this example with AI as 1 for all i's, the Nash equilibrium coincides with the social optimum for this game. Using another type of a game, we here use a cost function which is nonlinear, which is similar to the LQ game cost function, except that AI has been substituted by a function which depends on the neighborhood interactions as well, given by gamma I. And using the conditions where we want X star equal to Y star, that is the Nash equilibrium matches with the social optimum, we can find similar conditions for this type of game as well. So now we try to use we move to the using the variational inequality formulation and comparing it with the network games. So variational inequality, as we know by definition, is the problem of finding X star, where fx star transpose x minus x star is positive. So this is essentially a convex optimization problem, and as we have seen before, like the Nash equilibrium is also a minimization problem for the cost function. We can use this connection between variational equality and Nash equilibrium, where the Nash equilibrium X star solves the variational equality formulation where for function f, where f is the gradient of the cost function j with respect to its own strategy x. Similarly, for social optimum, we can define the cost function as we have defined the cost function as the sum of j's. We can use variational equality to find y star by using this formulation similarly. In the previous literature and in our references, we have seen the conditions for existence and uniqueness of Nash equilibria in network games through VI framework, and they have been presented and been generalized for network games. Um, and we have seen that these properties of Nash equilibrium, like existence, uniqueness, stability, depends on these properties of the function f used in the variational equality. And then the conditions of these specific properties can be derived in terms of adjacency matrix G using this connection. So we have used this technique to derive similar properties for conditions on social optimum and then extending it to our objective of socially optimum Nash equilibrium. For socially optimum Nash equilibrium, we use the VI formulation as shown previously with now the function being fx and wx together. So this is our first result, which states that the socially optimum Nash equilibrium on networks is unique for an LQ game if 2 minus 3 times 2 norm of G is positive, where 2 norm of G is the spectral norm of the adjacency matrix. And here we have seen, here the proof of this comes from the, uh, can be derived using using the property of VI formulation, which gives a unique solution for x star when the function f is strictly monotone. And here our function f can be using the strictly monotone properties for our cost functions, we derive this condition. This condition then allows us to design a network resulting in a unique socially optimum Nash equilibrium. Our second result is also states that the socially optimum Nash equilibrium for the LQ games is unique when this another condition 2 minus 2 times G infinity norm plus G1 norm is positive, where G infinity is the maximum absolute row sum and G1 norm is the maximum absolute column sum of the adjacency matrix. Using the assumptions on cost function, which we apply for the LQ game, the VI formulation gives a unique solution for x star when f is a block P function. So we use the property of VI formulation of uniqueness of the x star for when f is a block P function. And this condition again can allow us to design a network resulting in unique socially optimum Nash equilibrium presented in terms of the adjacency matrix properties. Robustness and continuity. So the next part that we talk about is how robust is this coincidence of Nash equilibrium with the social optimum? And in other words, if we try to perturb the adjacency matrix G, where the Nash equilibrium is socially optimum as well, then what happens to this social cost at the perturbation? And in our references and in previous literature, it has been proved that the Nash equilibrium itself varies continuously as a function of G when G satisfies certain conditions. So using that idea, we prove that the social cost also is continuous when the G matrix has undergoes perturbations under certain conditions of G. And this social cost is continuous when G satisfies either one of these two conditions, either 1 minus G 2 norm is positive or 1 minus G infinity norm is positive. So using this earlier example where we showed for the case of n equal to 4, the 2 norm of G satisfies the condition for continuity. And then we simulated the social cost function and the perturbations of G as shown here. And we can see there is continuity of social cost across the perturbations except where finding the Nash equilibrium is not possible. Another concept that we verified is the individual rationality constraint, where each individual player prefers participating within the design game to not participating. And this is satisfied for the LQ game with socially optimum Nash equilibrium. This over here, the players would want a positive outcome from the game rather than negative outcome, and that's when they would prefer playing. um, an extension of this work is the direction where we would like to see is in the large random networks. As in the case of real world applications, we have interactions which are where n tends to a large number, and characterizing the conditions on these networks for socially optimum Nash equilibrium, even approximately, can help us identify the networks which are beneficial to the society. Thank you, everyone. Thank you for this opportunity and coming and listening to my presentation. I thank the organizers at CISS for giving me the chance to present my paper, and thank you everyone to listening. Um, if you have any questions, you can reach out to me at the information mentioned earlier as well. Thank you. Have a great day.